Currently, well past Earth and its shadowed influence, a telescope silently observes the cosmos. From its remote, frigid observation point, the James Webb Space Telescope is doing more than just recording visuals in a manner unprecedented by any prior device. It is progressively unveiling the strata of universal antiquity. For many decades, scientists of the stars held the conviction that the cosmos, while immense, was quantifiable in its potential disclosures. Spanning approximately 14 billion light-years in all directions, this premise started to crumble the instant Webb focused on areas that seemed utterly void. Rather than finding emptiness, it revealed galaxies forming remarkably early, black holes expanding more rapidly than our current theories predict, and massive formations appearing when the cosmos ought to have still been in its nascent stage. The most disquieting consequence is not merely the extent of Webb's vision. It is what these findings suggest regarding the actual magnitude of reality and the proportion of the cosmos that might forever elude our grasp. Should you be prepared, accompany us as we reveal the insights provided by the James Webb Space Telescope. On this occasion, let us start to comprehend the genuine disclosures of the James Webb Space Telescope. We must relinquish one of our most reassuring presumptions concerning existence, the idea that when we gaze into space, we are observing the universe precisely as it is at this very moment. During our daily existence, sight appears instantaneous. Light traverses a space with such rapidity that your mind processes observation as immediate. The interval separating an object from your recognition of it is quantifiable in nanoseconds. This is significantly less than anything we perceive or consider relevant. The cosmos functions independently of human dimensions. Light propagates at an unvarying velocity, approximately 300,000 kilometers each second. No entity within the cosmos surpasses this speed. Such a velocity appears ultimate until distances become sufficiently vast to transform even light into a sluggish conveyor of information. From the instant light departs an object, it commences conveying historical data. Observing the moon means you are perceiving it as it existed 2 seconds earlier. The sun is observed in a state from 8 minutes prior. Should the sun cease to exist at this very moment, the heavens would persist in radiating light without alteration for a complete 8 minutes from our solar system's vantage. These temporal lags extend for several years. The closest star apart from our sun is perceived in a condition from over 4 years in the past. Upon observing the Milky Way's core, astronomers detect photons that commenced their voyage approximately 26 millennia ago, well preceding the advent of farming or recorded chronicles. Distance does not merely divide physical entities, it segregates temporal instances as optical instruments peer deeper into space. The cosmos ceases to function as a mere location and begins to operate as a chronological sequence. Proximate celestial bodies disclose the immediate past, whereas remote galaxies unveil progressively more ancient epochs of universal development. Consequently, the nocturnal firmament is not a real-time depiction of actuality. Rather, it constitutes a chronicle where each luminous point bears the imprint of its departure time. Each individual photon serves as an emissary that has endured an extensive voyage through the void. The greater the distance traversed, the more ancient the data it conveys. Nevertheless, these communications do not reach us in their original state. The cosmos is undergoing expansion. This is not due to matter propelling itself into a vacuum, but rather to the fabric of space itself distending between galactic clusters across eons. This subtle enlargement modifies all entities traversing it. This encompasses light, as the expansion of space causes wavelengths to extend concurrently. Vigorous blue and ultraviolet radiation transitions towards the red end of the spectrum, subsequently progressing into infrared. This phenomenon, termed redshift, is not an optical illusion. It represents a tangible quantification of the universe's expansion throughout the light's propagation. Redshift effectively transforms light into a temporal gauge. A greater elongation of the wavelength signifies a longer duration of light's transit and an earlier point of emission within the universe's chronology. Space and time are intrinsically linked. Observing further into the cosmos means peering further into the past. Throughout much of modern astronomy, a challenge arose. Initial telescopes were built mainly to view visible light, the limited spectrum our vision developed to perceive. Tools such as Hubble transformed astronomy, uncovering intricate structures and movements within proximate galaxies and nebulae. However, as scientists extended their gaze towards the universe's genesis, the cosmos seemed to become less dense. This wasn't due to emptiness, but rather a transformation in its light. The initial galaxies emerged within a warmer, more compact universe, emitting vigorous and luminous light. Yet as this light traversed an expanding cosmos, it was elongated well past the visible spectrum. Upon its arrival at Earth, a significant portion of it manifested solely as infrared energy. These areas appeared dim to telescopes designed for visible light. This apparent darkness was misleading. It wasn't a void, it was simply unseen. The James Webb Space Telescope was constructed to perceive what previous devices were incapable of detecting. Right from its inception, Webb was conceived as an infrared observation facility. Its primary mirror extends over 6 meters across. Composed of gold-plated segments, it was selected for its effectiveness in reflecting infrared radiation. Nevertheless, its placement holds equal importance to its dimensions. Webb does not circle our planet. It functions almost 1,000,000 miles distant, positioned at a gravitationally stable point, allowing it to stay constant and unperturbed. This separation enables a crucial function. It permits the Webb telescope to achieve extreme coldness. Infrared radiation has a strong connection to thermal energy. Every warm entity emits infrared light. Even a marginally warm telescope would overpower the subtle cosmic signals it endeavors to observe. Consequently, Webb was designed to be thermally invisible. A substantial, multi-layered sun shield obstructs warmth and illumination from the sun, earth, and moon on its shaded aspect. The instrument chills to such low temperatures that its own structural emissions diminish, allowing only the subtle traces of primordial light to remain, leaving solely the subtle echoes of primordial illumination. Solely within this stillness can the nascent universe be perceived. When Webb directs its gaze towards a seemingly vacant celestial area, it is not seeking an absence. It is patiently awaiting, anticipating photons that commenced their voyage eons ago. These photons, attenuated by cosmic expansion and diminished by the passage of time, arrive gradually, occasionally individually. Webb might scrutinize the identical celestial segment for extended periods, diligently gathering primordial light that traversed almost the entirety of the observable cosmos. Every photon conveys data from an unrepeatable instant. Once these photons are ultimately compiled into an image, the outcome differs from what initial cosmology anticipated. The nascent universe does not present itself as faint or delicate. Instead, it seems vibrant. Galaxies materialize where none were foreseen, and stellar systems are already in the process of formation. Configurations are rapidly coalescing. Rather than a tranquil genesis, Webb uncovers a universe that was bustling from its very inception. This aspect is profoundly humbling. The pictures captured by Webb are not mere current-day photographs. Each individual image represents a vast tapestry of ancient time, composed of light that originated eons prior to Earth's formation. Before our sun began to shine, and before the Milky Way galaxy assumed its present shape, whole eras of universal development transpired as that light journeyed through space. When Webb finally observes this light, the occurrences it chronicles have concluded ages ago. These events are impossible to re-examine or modify. They persist solely as fixed instances captured mid-journey. Consequently, astronomers assert that the James Webb Space Telescope doesn't just peer into distant regions, it gazes into the past. Spatial separation transforms into a chronological sequence. Objects in proximity display the universe as it was more recently, while remote celestial bodies disclose progressively earlier phases of cosmic development, stacked one behind the other. Nevertheless, even Webb's remarkable observational capability possesses boundaries. No instrument can observe past a certain limit, which is established not by technological constraints, but by the fundamental laws of physics. This demarcation is determined by the maximum distance light could have traversed since the cosmos originated. This region is known as the observable universe. This particular limit does not signify a spatial extremity. Rather, it marks the extent of accessible data. Space extends further beyond this point. Galaxies continue to form, stars are born and perish, black holes coalesce. Complete universal narratives transpire outside our perception. This isn't due to an absence of viewing instruments, but because the ongoing expansion of space hinders their light from ever reaching us. The James Webb Telescope has not uncovered the ultimate boundary of existence. Instead, it has shown us the vast extent of reality that remains beyond the scope of any possible observation. As Webb approaches this frontier, identifying galaxies that are older, more luminous, and more plentiful than anticipated, a profounder consequence starts to surface. Should the cosmos already exhibit such richness and organization at the extreme edges of our visibility, then the actual magnitude of all that exists must considerably surpass the observable segment we inhabit. Webb isn't simply completing absent information. It is demonstrating that the universe accessible to our observation might represent just a tiny, fortunate glimpse into an immeasurably grander entity. A repository of photons, suggesting narratives that will forever stay undiscovered. For many years, scientists held a rather conservative view regarding the initial periods of the universe. Following the Big Bang, the cosmos underwent swift expansion, temperatures decreased, and material dispersed nearly uniformly. Gravitational force was present but initially feeble, gradually working to magnify minute inconsistencies remaining within the nascent universe. According to that model, the primordial universe wasn't void, yet it was rather quiescent. Gas required a period to cool, dark matter concentrations needed time to develop sufficiently large to ensnare conventional matter, and stars took millions of years to commence fusion. When galaxies eventually emerged, they were anticipated to be diminutive, faint, and delicate groupings of stars, merely starting to coalesce, requiring hundreds of millions of years to fully develop. This particular assumption influenced numerous cosmological theories over time. The nascent universe was envisioned as an extended preparatory stage, a slow progression from basic forms to intricate structures. Upon the James Webb Space Telescope commencing direct observations of that epoch, scientists anticipated corroboration. However, what they discovered was a discrepancy. Webb examined periods less than 500 million years post-Big Bang, times when the cosmos had reached only a small fraction of its present age. Within those areas, theoretical predictions suggested rarity, a mere scattering of dim galaxies across a predominantly dark universe. What Webb actually observed was profusion. Luminous galaxies emerged repeatedly, not as infrequent exceptions but as a consistent trend. These cosmic structures weren't just barely stable, they were actively generating stars at astonishing speeds, emitting light in amounts that ought to have taken considerably longer to generate. The surprising aspect wasn't a solitary entity. It was their sheer abundance. A number of these nascent galaxies seemed to encompass hundreds of millions or even billions of solar masses and stellar content. Per established theories, accumulating such a vast quantity of matter ought to have consumed much more time than the universe's age when that light was released. While gravity possesses immense strength, its effects are not instantaneous. Gaseous matter doesn't undergo immediate collapse. It needs to shed energy and decrease in temperature. Dark matter must undergo condensation. Halos expand via fusions and a more gradual accumulation process. Stars are required to originate and complete their lifespans. Occasionally, they perish prior to supplying matter for subsequent generations. Every stage brings about a postponement. Nevertheless, Webb observed galaxies that gave the impression that numerous such stages had already transpired. What rendered the finding even more perplexing was not merely the luminosity of these galaxies, but their seemingly advanced chemical composition. Webb identified spectroscopic traces of elements such as carbon and oxygen. Additionally, nitrogen was found in certain of these nascent systems. These particular elements are not leftover products from the Big Bang. They are created within stars. Carbon develops within the central regions of stars. Oxygen originates from colossal stars and disperses into the cosmos upon their explosive demise. Nitrogen necessitates an even greater degree of refinement. Their existence signifies an undeniable truth. A minimum of one prior stellar generation must have already come into being, existed, and ceased to exist, all within the initial several hundred million years of the universe. This drastically condenses the timeline of cosmic events. It implies the universe accelerated through stages we had presumed would progress at a leisurely pace. Similar to a book, where the initial sections were bypassed to arrive at the midpoint. To grasp why this profoundly disturbed astronomers, it's beneficial to consider it from a construction perspective instead of an astronomical one. The formation of a galaxy isn't a solitary act, it's a progression. One cannot erect towering buildings before infrastructure like roads is in place. It's impossible to lay concrete before steel has been manufactured. You cannot establish communities. Prior to the establishment of foundations, the nascent universe was presumed to be in the process of laying them. Webb, however, discovered structures that were already fully formed. With the accumulation of these findings, investigators informally started calling the issue too much light, too early. When astronomers computed the expected total starlight within the universe's initial billion years, their forecasts consistently underestimated Webb's observations. Occasionally by double, sometimes by significantly more. This wasn't a minor inconsistency that could be disregarded. It indicated that a foundational aspect of the existing models could be lacking. Researchers reacted with prudence, as is their custom. They pondered if the luminosity of the galaxies had been misunderstood. Might cosmic dust be influencing the readings? Could gravitational lensing be amplifying remote galaxies, causing them to seem more brilliant and substantial than their actual state? These effects are real, and accounting for them helped mitigate the most extreme instances, but they failed to eliminate the underlying pattern. Repeatedly, Webb observed distinct cosmic regions using various instruments and wavelengths. Each time, the nascent universe appeared densely populated and brightly lit. Star formation was not struggling to commence, it was flourishing. This compelled astronomers to reevaluate a fundamental assumption: the efficiency with which the universe converts gas into stars in the present era. Currently, star formation is remarkably inefficient. The majority of gas within galaxies never transforms into stars. Instead, it is heated and agitated by turbulence. It is either repelled by radiation or expelled by stellar winds. Only a small fraction condenses into new suns. The early universe seems to have operated under different principles. Density is one potential explanation. In its early stages, the cosmos was more compact, with matter packed more tightly. Gas clouds collided more frequently, increasing the probability of collapse. Another possibility is composition. The initial generations of stars formed from nearly pure hydrogen and helium. Without heavier elements to complicate the cooling process, mergers likely also played a significant role. In the young universe, galaxies were closer together, and collisions were common. When galaxies coalesce, gas is driven inward, compressed to extreme densities, triggering intense bursts of star formation. While each of these factors helps explain a part of the phenomenon, none fully accounts for it. At the core of many of these early galaxies lies another enigma that deepens the mystery: black holes that appear far too massive for their age. Webb has detected evidence of supermassive black holes already present when the universe was less than 500 million years old. Some of these objects possess masses millions, even billions of times that of the Sun. According to conventional models, this should be exceedingly difficult. Black holes formed from collapsing stars begin small, typically only tens of solar masses. While they can expand by consuming surrounding matter, that growth is limited because as material falls in, it heats up and releases enormous energy, producing radiation that pushes additional matter away. This establishes a natural growth limit, yet Webb continues to find early black holes that seem to have effortlessly surpassed this boundary. To explain them, astronomers have been forced to consider scenarios once deemed exotic. Perhaps some black holes formed through the direct collapse of massive gas clouds, entirely skipping the stellar phase. Perhaps the first stars were considerably more massive than those we observe today, collapsing into larger black holes from their inception. Alternatively, the nascent universe might have simply allowed growth to occur more rapidly. None of these hypotheses has yet been confirmed, and none can be dismissed. What is clear is that these primordial black holes are not rare exceptions. They appear alongside the luminous galaxies Webb consistently discovers, suggesting a potential link between swift galaxy formation and accelerated black hole expansion. And that connection holds significance. These nascent galaxies did not merely exist in isolation. Their radiation profoundly reshaped the universe. Their ultraviolet light ionized the ambient hydrogen, transforming the cosmos from an opaque haze into a transparent medium. Their supernovae dispersed heavy elements throughout space, and their gravitational pull initiated the sculpting of large-scale cosmic structures. Should their formation have occurred sooner and more rapidly than anticipated, then the whole chronology of cosmic development is altered. Phenomena previously believed to manifest at a later stage now need to be placed nearer to the genesis. Mechanisms once thought to necessitate a prolonged, gradual development could instead arise from exceptionally harsh initial states. Such findings do not imply the cosmos defies our theoretical frameworks. Rather, they suggest our current theories might yet be lacking. As Webb's gaze penetrates further, the more challenging it grows to disregard this recurring phenomenon. The nascent cosmos shows no signs of being hesitant or sluggish. Its conduct is unlike that of a meticulously planned building endeavor. Instead, it acts as if matter surged, material swiftly condensed, and stars sparked into existence with great effectiveness. Galactic structures formed with speed, massive black holes expanded concurrently. Intricacy manifested in the early stages, not later on. This understanding holds a significant consequence. Regarding the vastness of the cosmos, should intricate formations have developed with such efficacy close to the boundaries of our observational capacity, then the areas situated beyond those confines, territories forever hidden from our view, could possess an equivalent abundance, intricacy, and density of galaxies. The cosmos proceeded without delay. And if such extensive construction was already underway so early within our visible range, then the actual magnitude of what lies beyond that boundary grows even more challenging to comprehend. Webb's discoveries extend beyond merely identifying more luminous galaxies. It has demonstrated that the initial phase of the universe was considerably more vigorous than previously conceived, compelling a reevaluation of the speed at which existence began to self-organize. Throughout a significant portion of the 20th century, astronomers felt they were nearing a resolution to one of humankind's most profound inquiries, namely, the total number of galaxies present in the cosmos. The methodology was straightforward in theory, though arduous in practice. Direct a potent telescope towards a seemingly vacant segment of the firmament, enumerate each galaxy discernible within that minute area, subsequently presuming that segment to be typical and extrapolating the count to encompass the entirety of the heavens. During the Hubble Space Telescope's most profound observational endeavors, the outcome proved astounding, even within a celestial expanse no bigger than a single grain of sand viewed at arm's length. Myriads of galaxies became visible within those captured visuals. Cosmologists calculated that the discernible cosmos encompassed several 100 billion galaxies. This figure was so immense it scarcely conveyed tangible significance. For an extended period, this remained the recognized measure of universal plenitude. Subsequently, the James Webb Space Telescope peered into comparable obscurity and subtly introduced new complexities. While previous deep-field photographs displayed voids between remote, indistinct blurs, Webb uncovered subtle formations stacked one behind the other. Whole communities of galaxies came into view, not due to recent formation, but rather because their emitted radiation had shifted into infrared spectra, undetectable by earlier instruments. This represented not a marginal adjustment, but a significant amplification. Webb's profound field surveys redefined the concept of vacant cosmic regions. Areas formerly believed to hold only a handful of dim galaxies now present as densely packed, teeming with successive epochs of systems extending almost to the universe's genesis. During one of its most extensive deep sky investigations, Webb scrutinized a celestial area marginally exceeding the combined size of 3 full moons. Accumulating data over hundreds of hours, it gathered subtle infrared light particles, layering successive exposures, thereby constructing an image from radiation that had journeyed for eons. Upon the amalgamation of the collected data, the magnitude of the revelation proved astonishing. Hundreds of thousands of individual galaxies. The field of view was populated by galaxies, not individual stars. Every single one a stellar metropolis housing millions, billions, or occasionally trillions of solar bodies. Numerous planetary systems exist. A considerable number of them have already gone through multiple cycles of star creation and extinction. Many are abundant in cosmic dust and heavy elements formed throughout vast stretches of time. It turns out the universe is not sparsely filled with isolated celestial bodies drifting through the void. It is teeming with celestial bodies. The particular strength of Webb's contribution lies not merely in the vast quantity of galaxies it uncovers, but in the detailed data it gleans from every single one. Webb doesn't just identify luminous spots, it gauges their hues across infrared spectra, enabling astronomers to calculate distances, masses, rates of star formation, and approximate ages. Consequently, every galaxy serves as a data entry within an immense chronological record. As researchers started compiling these data entries, a distinct pattern became apparent, one theorized for many decades yet never witnessed with such precision. Galaxies are not dispersed haphazardly. Instead, they congregate, they orient themselves, outlining colossal formations throughout space, creating extended filaments spanning tens and hundreds of millions of light years. These thread-like structures converge at concentrated points, serving as sites for the formation of galaxy clusters, whereas immense areas separating them are nearly devoid of matter. This arrangement is referred to as the cosmic web. Previous telescopes had offered glimpses of this, but Webb now fully uncovers it. It brings to light whole groups of dusty galaxies, previously unseen, suddenly bridging the voids and linking filaments that once seemed disconnected. The cosmic network appears unbroken, complex, and undeniable. This arrangement serves a purpose beyond mere ornamentation. It serves as an account of the universe's development following the Big Bang. Matter was spread nearly evenly throughout space, with minute density fluctuations established during the cosmos's initial phases. Areas possessing marginally greater density exerted a somewhat more potent gravitational attraction. Gradually, matter migrated towards these zones, thereby intensifying the disparities. A helpful comparison can be made to precipitation on irregular landscapes. Water doesn't exclusively descend into rivers, it lands universally, yet gravitational force draws it downwards, sculpting conduits and depressions while leaving elevated areas parched. Eventually, an organized topography takes shape. Within the cosmos, gravitational forces performed an identical function. Material gravitated into these filaments and nodes, thereby depleting adjacent areas and creating immense empty spaces. Webb's findings indicate that this phenomenon commenced in the early universe. Thread-like formations, spanning tens of millions of light years, were already present when the cosmos was merely a few billion years old. Certain structures exhibit an astonishing degree of organization for their epoch, prompting a re-evaluation of theories regarding the speed at which matter can self-organize across such immense dimensions. A particularly notable instance is a galactic chain extending beyond 10 million light-years, identified within the nascent universe. Numerous galaxies are situated along a solitary filament, linked together akin to pearls on a cosmic thread. A number of its most massive constituents have ceased star formation, a condition atypical for such an early epoch. This implies that the surrounding environment is crucial. Galaxies developing in concentrated areas progress dissimilarly compared to those in isolation. Numerous interactions and fusions hasten their developmental stages. Gaseous material is rapidly depleted, potentially leading to an early cessation of star creation. Webb has empowered astronomers to pinpoint countless galaxy groupings and nascent clusters throughout cosmic history. By contrasting assemblages at varying distances, researchers can effectively observe the evolution of structure from small galactic associations to the colossal clusters visible today, unfolding over eons. Such an uninterrupted perspective was previously unattainable. Nevertheless, despite all this concentration and order, the cosmos is equally characterized by its vast void. Immense empty spaces spanning tens to hundreds of millions of light-years and containing extremely few galaxies are situated between the threads of the cosmic network. These vast empty zones are far from being minor interstices. These entities occupy the vast majority of the universe's volume. Were you to be situated at the core of one, gazing in any direction, you would perceive an expanse of darkness extending for tens of millions of light-years prior to encountering the closest galaxy. Vast cosmic areas remain devoid of accumulated matter, solely because gravitational forces drew that material to other locations. Webb's deep field photographs vividly illustrate this striking contrast. Compact clusters of galaxies emerge adjacent to vast, empty expanses that contain virtually nothing. The cosmos, therefore, is simultaneously densely packed and largely vacant. This dual nature fundamentally alters astronomical perspectives on cosmic scale. Enumerating galaxies transcends mere object tabulation. It now involves comprehending their spatial arrangement, their tendency to cluster, and the immense voids separating them. Upon astronomers extrapolating Webb's deep field observations to encompass the entirety of the celestial sphere, the figures shift significantly. The aggregate quantity of galaxies within the observable cosmos might not merely reside in the hundreds of billions. Instead, it could reach into the trillions. Such an escalation carries significant ramifications. An increased number of galaxies translates to a greater abundance of stars, which in turn signifies a higher count of planetary systems. A larger quantity of planets then presents more avenues for intricate developments to emerge. The cosmos expands beyond mere physical dimensions. It also grows richer in potential. However, even this vastness is confined solely to the observable universe. This refers to the cosmic expanse from which photons have been able to travel to us since the dawn of the universe. Past that demarcation, space persists and cosmic structure endures. Galaxies persist in their formation and evolution into intricate networks. Webb's deep fields offer clues to this phenomenon by demonstrating that even close to the boundaries of our observational capacity, the cosmos maintains a high density of objects. No indication exists of a decrease in density as one approaches a boundary, a notion that provokes a disquieting reflection. Should reality be this populous within the segment accessible to our observation, then the actual magnitude of all that lies beyond could far exceed even our most liberal projections. Attempting to quantify the immeasurable does not yield a definitive total. Rather, it exposes the profound incompleteness of our viewpoint. Webb has not concluded the cosmic inventory. Instead, it has demonstrated that such an enumeration might be perpetual. Furthermore, what we previously considered almost finalized might merely have constituted the initial phase. Superficially, the cosmos appears straightforward to quantify. The Big Bang event took place approximately 13.8 billion years in the past. Photons propagate at an unvarying velocity. It appears intuitive to presume that the farthest observable entities ought to be situated roughly 13.8 billion light-years distant. However, that particular intuition proves profoundly deceptive. The portion of the universe accessible to our observation is considerably more expansive than its chronological age would imply. Its radial extent measures not 13.8 billion light-years, but rather approximately 46 billion light-years, resulting in a total diameter of roughly 93 billion light-years. This figure is neither a mere conjecture nor a linguistic artifice. It arises as a direct consequence of the intrinsic behavior of space itself. The misunderstanding originates from our conceptualization of motion. No entity can traverse space at a velocity greater than that of light, and this fundamental principle remains valid. No galaxy is violating any universal velocity constraint. nor is any signal surpassing the laws of physics. Rather, the cosmos expands in a more subdued and considerably more enigmatic fashion. The fabric of space itself undergoes expansion. When astronomers state that remote galaxies are receding from our vantage point, it is tempting to visualize them propelling outwards akin to fragments from an explosive event. However, at grander scales, galaxies aren't moving through the cosmos from a central origin. Instead, they're being separated as the intervening space expands. A straightforward comparison aids in understanding this. Picture points marked on a balloon's exterior. When the balloon expands, each point distances itself from all others, not due to the points gliding over the surface, but because the surface itself is growing. No single point occupies the middle. None holds a unique status. Each point observes all others receding. The cosmos operates in a very similar fashion. At the time a far-off galaxy released the light we perceive currently, it was considerably nearer to us than its present location. For eons, as that light journeyed towards Earth, the expanse separating us and the galaxy steadily grew. Upon the light's arrival, the galaxy from which it originated had been transported tens of billions of light-years further. This explains why we can view galaxies whose illumination has been journeying for over 13 billion years, despite their present separation being much larger than 13 billion light-years. Light isn't traversing an unchanging span, it's progressing through a distance that lengthens as it journeys. Essentially, light is operating on a universal conveyor belt. During the cosmos's nascent stages, its expansion proceeded more slowly, allowing light to advance consistently. With the passage of time, this expansion quickened, elongating distances at an increasing rate. Certain photons succeeded in reaching us because they commenced their voyage sufficiently early. Others never shall. This establishes a demarcation, neither a barrier nor a limit, but a boundary, the universal horizon. The universal horizon denotes the extent of what can ever be perceived from our vantage point, considering the cosmos's finite age and how space expands beyond that point. Light fails to reach us not due to a lack of time, but because the region it needs to cross expands more rapidly than light can travel through it. Herein lies the disquieting aspect of the universe's magnitude. Space doesn't terminate at the universal horizon. We understand this as the cosmos appears fundamentally uniform. From all perspectives, we notice that the quantity of galaxies doesn't diminish towards a boundary. The subtle residual glow from the nascent cosmos presents itself almost evenly throughout the heavens. Such consistency would be challenging to account for if space suddenly ceased just past our line of sight. Thus, the universe stretches beyond our perception, yet it does so in a manner that perpetually conceals a significant portion of itself. Past the visible horizon, galaxies persist, stars keep forming and expiring, and black holes coalesce. Complete universal narratives develop in areas that will never affect us and can never be affected by us. No transmission from those locales will ever arrive on Earth, not due to limitations of our equipment, but because space-time itself impedes the data's arrival. What's even stranger is that this demarcation isn't static. With the progression of time, the perceivable universe expands, as light from farther areas has had additional time to reach our location. The boundary gradually extends outwards. Concurrently, the cosmos's expansion is quickening, leading distances to elongate more rapidly now compared to previous times. These two phenomena contend with each other. The outcome is a cosmos where certain entities become visible for a short period, merely to subsequently vanish from our grasp permanently. Galaxies currently within our sight are not assured to stay observable. Their illumination keeps elongating, transitioning into extended wavelengths, growing fainter and more diffused over time. From our viewpoint, those galaxies seem suspended at a specific instant in their past. We perceive them in their past state, not in their ongoing transformation. Their subsequent development, their fusions, their alterations and ultimate destiny might be data that will never reach us. This isn't a remote theoretical concept. This is a direct consequence of the observed expansion rates. Should the universe maintain its current behavior, then in approximately 100 billion years, all galaxies beyond our local, gravitationally bound area will pass beyond the cosmic horizon. Observers in the distant future would perceive a cosmos comprising solely a small cluster of nearby galaxies enveloped in darkness. They might never become aware that anything else had ever existed. This alters the very definition of observation. The observable cosmos is not the entirety of the universe. Rather, it is merely the segment of the universe visible from our current vantage point at this specific moment in cosmic time. Should one relocate to a different galaxy, the observable cosmos transforms. New regions come into sight, while others recede beyond the visible horizon. Each spatial location establishes its unique observable sphere. This gives rise to peculiar yet inescapable implications. It's possible for two galaxies to be simultaneously visible from Earth, yet incapable of observing one another. This is because they might reside on opposing sides of our cosmic horizon. While light from both reaches our location, the light from one can never traverse the distance to the other. From their respective viewpoints, Earth itself could potentially be situated beyond their own cosmic horizon. No singular advantageous viewpoint exists, no central position, no location from which the entirety of the cosmos is simultaneously visible. Each observer occupies the core of their unique observable universe, circumscribed by boundaries imposed by cosmic expansion and the passage of time. This underscores the significance of venturing further into space. Every fresh discovery made close to the horizon. It represents more than merely uncovering an additional galaxy. It signifies an encounter with the very boundaries of human understanding. The galactic structures observed at immense distances are no longer situated at the point where their emitted light originated. They have receded considerably during that light's journey. Our observations reveal a historical trace rather than a present-day position. What becomes visible to us is not the current reality, it is a reflection of what once was. Past the visible horizon extends the unobservable cosmos. These are areas that could harbor structures equally as rich and intricate as those within our view. Certain cosmological models propose an infinite universe. Conversely, other theories posit it as finite, yet immeasurably immense. In any case, the visible cosmos constitutes almost certainly merely a segment of the entirety. The James Webb Space Telescope has not unveiled the universe's boundary. Instead, it has demonstrated the absence of any accessible edge whatsoever. What exists is merely a continuously shifting horizon and a reality stretching far beyond anything light could ever convey to us. During the 20th century, cosmological understanding was founded upon a straightforward premise. The cosmos originated with the Big Bang, then expanded outwards, with gravity promptly commencing its efforts to decelerate that expansion. The paramount unresolved query was not concerning gravity's relevance, but rather its ultimate triumph. Would the universe continue its eternal expansion, dissipating into obscurity? Or would gravity someday invert this process, drawing all matter back into a unified state? Each iteration of that discussion operated under the identical presumption that gravity held sway. That premise failed to withstand observational scrutiny. Towards the close of the 1990s, astronomers commenced investigations into remote stellar detonations. Referred to as Type Ia supernovae, these phenomena transpire when a white dwarf star attains a critical mass and subsequently explodes. Each instance yields an explosion possessing nearly identical intrinsic luminosity. Due to this remarkable uniformity, Type Ia supernovae serve as reliable cosmic distance indicators. Astronomers determine the distance of these explosions by observing their apparent brightness from Earth. When this distance is combined with the recession speed of its host galaxy, the universe's expansion history starts to become clear. The data revealed a stark truth. Remote supernovae appeared fainter than anticipated. Their associated galaxies were located at a greater distance than predicted, assuming cosmic expansion was decelerating due to gravity. The universe wasn't slowing down. Instead, its acceleration increased with observational distance. This pattern grew increasingly evident. Expansion hadn't just persisted since the Big Bang, it had been gaining speed for eons. An unknown force was driving space apart, overcoming gravity's influence on vast scales. To explain this phenomenon, cosmology had to incorporate a novel element into its calculations: dark energy. Dark energy is imperceptible to direct observation. It neither emits, bounces, nor takes in light. It also doesn't aggregate into celestial bodies like stars, planets, or galaxies. Its presence is deduced solely from its impact on space, an effect that governs the universe. Data suggests dark energy constitutes approximately 70% of the cosmos's overall energy composition. Common matter, encompassing all known entities from atoms to galaxies, comprises under 5%, whereas dark matter constitutes the majority of what's left. The observable universe represents a small fraction of its own narrative. What renders dark energy particularly perplexing is its conduct as the cosmos grows. Conventional matter becomes less dense as space expands. If the spatial volume doubles, matter's density is halved. Electromagnetic radiation dissipates at an even quicker rate. Dark energy, however, defies this principle. Its concentration seemingly stays uniform despite spatial expansion. Consequently, as the universe expands, the overall quantity of dark energy rises. Increased space generates additional dark energy, which in turn propels quicker expansion, leading to even more space. This forms a subtle, self-reinforcing cycle. During the initial billions of years following the Big Bang, matter held sway over the cosmos. Gravity shaped its architecture, drawing matter together into galaxies, clusters, and cosmic filaments. Cosmic expansion persisted, yet it decelerated somewhat due to gravitational opposition. Approximately 5 billion years ago, this equilibrium changed. With matter growing progressively dispersed by expansion, dark energy surpassed its dominance thereafter. Expansion started to speed up, and gravity's effect on grander scales commenced diminishing. The cosmos transitioned into a different era. While the James Webb Space Telescope cannot directly observe dark energy, its telltale signs are ubiquitous. Webb observes its effects in the significant redshift of ancient light, the vastness of the visible universe, and how remote galaxies dim and move away. Dark energy's impact is evident throughout the heavens. Were it not for dark energy, the universe would be considerably more compact. The cosmic boundary would be situated significantly nearer. Furthermore, extensive areas of space currently visible to us would have remained unseen. Dark energy doesn't merely influence the present, it dictates what's to come. Should dark energy maintain its consistency, as indicated by present data, then expansion shall persist indefinitely. Gravity will continue to bind galaxy clusters, yet all beyond them will slowly separate. Trillions of years from now, as cosmic horizons are individually traversed, observers situated within a galaxy akin to the Milky Way would perceive a universe populated solely by nearby stars and little else. The vast cosmic web would recede entirely from view. The very indicators of the Big Bang would dissipate, their wavelengths elongated to an undetectable extent. The cosmos would continue to exist, yet it would seem nearly vacant. This fact alone would be troubling, yet Weber brought an even more significant issue into sharp relief. When scientists gauge the current expansion velocity of the universe, they fail to arrive at a unified figure. Two distinct results emerge. One technique investigates the distant past, analyzing the cosmic microwave background, which is the faint residual glow from when the universe was approximately 380,000 years old. From the delicate patterns within this radiation, scientists infer an expansion velocity of roughly 67 kilometers per second per megaparsec. The second approach examines the local universe. Astronomers ascertain distances to galaxies by employing variable stars and type Ia supernovae, subsequently correlating these distances with the speed at which galaxies are receding. This methodology consistently yields a higher numerical value. Registering around 73 kilometers per second per megaparsec, both sets of measurements are highly accurate. They have each been replicated and subjected to rigorous scrutiny, but they fail to align. This divergence is referred to as the Hubble tension, and it signifies one of the most critical fissures within contemporary cosmology. The rate of cosmic expansion dictates the universe's age, its spatial extent, and its eventual fate. Should our understanding of this be incorrect, numerous conclusions reached over several decades may necessitate reconsideration. The James Webb Space Telescope was anticipated to assist in alleviating this tension by improving distance measurements, especially those involving stars utilized for calibrating cosmic scales. Conversely, Webb's observations validated the higher expansion rate. The discrepancy, far from lessening, became more entrenched. This development leaves the field of cosmology confronting uneasy scenarios. An undetected flaw might be concealed within the data. Our foundational assumptions about the early cosmos could be incomplete, or novel physical principles, yet to be discovered, might be at play. One specific hypothesis posits that dark energy is not truly invariant, but rather its potency shifts throughout cosmic history. A further alternative suggests that the early universe operated dissimilarly to our current suppositions, leaving behind subtle vestiges that continue to impact contemporary expansion. Each of these potential scenarios carries weighty implications. Should dark energy undergo transformation, the universe's future state could appear markedly different from what is currently anticipated. In particularly drastic scenarios, dark energy might progressively strengthen, eventually overcoming gravity even on more localized scales. In the most extreme interpretations of this concept, expansion would not cease merely with the separation of galaxies. Galactic clusters would be fragmented, and the galaxies themselves would disintegrate. In the most remote future, even atoms could be torn asunder in an event sometimes termed the Big Rip. Existing evidence does not lend support to this specific outcome, though a measure of uncertainty persists. What is already evident is the pervasive dominance of dark energy throughout the cosmos. It expands the very fabric of space, obscuring immense portions of reality beyond every observable limit. It dictates what future observers will be able to perceive and what will forever remain beyond their knowledge. It accounts for the observable universe spanning nearly 93 billion light-years. It is also the underlying cause for the majority of reality remaining perpetually beyond reach, not solely due to technological constraints, but fundamentally. Yet, dark energy on its own cannot fully account for the universe we currently observe. This is because while it causes space to expand on larger scales, a different force must be responsible for drawing matter together on smaller ones. Something must facilitate the formation of galaxies, preventing their dispersal into a uniform void. This particular force is also unseen, equally enigmatic, and just as crucial for grasping how structure can endure within a universe that is being relentlessly pulled apart. We must direct our focus to the unseen framework that maintains galactic integrity, an invisible architecture that subtly molds everything we perceive. If dark energy dictates the universe's expansion, then dark matter governs its self-cohesion. Were it not for its existence, the cosmos observed through the James Webb Space Telescope would lack any discernible structure. Galaxies would not have coalesced and clusters would have scattered. The vast patterns outlined throughout the cosmos would never have manifested. Dark matter is not luminous. It neither takes in light nor gives off any form of radiation that we can directly perceive. Nevertheless, it surpasses all visible matter in mass by a ratio exceeding 5:1, constituting approximately 85% of the universe's total matter. This constitutes dark matter, whereas all conventional matter, stars, planets, gas, dust, and people, forms merely a minor fraction. What becomes apparent to us is not the fundamental framework itself, but rather the lit exterior of something more profound. Initial indications of dark matter surfaced well before the advent of modern telescopes. Astronomers observed galaxies exhibiting behaviors that contradicted established predictions.